Okay, I would like to introduce to you this modeling project, the effect of vaccination rates on multivariant COVID-19 prevalence among different risk categories. All right, so that's a mouthful. We'll explain what that means. Well, I'll explain it now. Vaccination rate, you know, one of the issues now is that many people are not getting vaccinated against COVID. We also know another issue is that a new variant, the Delta variant, has come on the scene. And so these are two important effects in the current COVID landscape. Sorry, this should be prevalence instead of prevalence, so I'll change this here. All right. Now, the other important thing is that some people are a very low risk of death from COVID, young people, healthy people, and so on. And some people are very high risk, elderly, people with diabetes, people who are obese, and so on. So often people who don't get vaccinated are healthy and have very low risk, while people who are high risk get vaccinated at a much higher rate. However, the people who don't get vaccinated still put the people at high risk at higher risk. So this project is to quantify the increased risk on high-risk people because of non-vaccination of low-risk people. All right, certainly very important question. All right, so these are questions to be addressed. How does vaccination rate of low-risk individuals affect infection rate of high-risk individuals? Okay, first question. So in scenarios where a new variant is introduced, so a variant is newly introduced, how does vaccination preparedness and or response affect the number of COVID infections of high-risk individuals? All right, so again, the situation when the Delta variant is introduced, how does this affect the high-risk individuals? So if you start vaccinating right away, or if you delay, or only half the people get vaccinated and so on, what are the differences? We also have vaccination booster. So we'll include vaccination booster in the model. Does this make a lot of difference? All right, so these three questions, we may add more. Once we get the model, we can ask a lot of questions. But this is guiding our formation of the model. All right. So in the usual assumption, when you do multiple compartment models, you have a homogeneously mixing population. What that just means is people are equally likely to contact other people. This is not like a network model where some people tend to go to schools or to workplaces and have higher contact rates with other people. This just says everybody's mixed together. An oversimplification, certainly, but one that's often used in mathematical modeling. Every model has some simplifications. You cannot make an entirely realistic model. You just try to capture as much of the situation as you possibly can without making the model too complicated. All right, so now at any time t, the total population is n of t, is divided into two subpopulations, low risk, indicated by the subscript n equals 0, and high risk, indicated by the subscript n equals 1. All right, so when you see the subscript n, that's referring to two subpopulations, low risk and high risk. 0 refers to low risk, 1 refers to high risk. High risk individuals include elderly, obese, and others with various health conditions that put them at increased risk of death from COVID, while low risk includes the rest of the population. All right, so again, this is a simplification, but one that can be helpful. All right, now, the total subpopulation sizes are n0 and n1. So we suppose these are fixed subpopulations. We assume that the population sizes are constant and there's no incoming or outgoing individuals, which is a good approximation in the short term. Within a couple months range or a year range, not too many people get born. Even if people die, it's a relatively small percent of the total. So it's not going to affect largely the results that we obtain. Now, the two subpopulations have the same compartmental structure, which is shown in the figure below. So our system actually has two copies of this diagram, one for low risk and one for high risk. For low risk, you'd put zeros here everywhere, and for high risk, you'd put ones everywhere. All right? All right, so here's the diagram, and this diagram will be explained below. And these funny symbols, this circle dot and other stuff here that's going on. All right. Now you should be able to recognize this. Here you have compartments, which represent different classifications of people. And here you have transition rates. For instance, this W means that to go from here to here, the rate is W. And we'll see that. So for instance, you'd have ds dt would have a term proportional to WNS, right? Or negative WNS. That's how this multi-compartment diagramming works. We've seen these diagrams before, so you can interpret all of these rates this way. For instance, this one here, the derivative of en dt is minus delta times en. That should be a delta n there. It's a little bit unclear, but I think you can infer that. Some of these have vectors over them. The e and the n have vectors. We'll explain what that means in a moment. I mean, you know what a vector is? Basically, that there are two components to this compartment. All right, so each subpopulation is further subdivided into several epidemiological states depending on an individual's health status. You have susceptible, SN. You have 3 stages of vaccinated, VN1, VN2, VN3. Exposed, these are people who have been exposed to the COVID. And will be, and they're kind of pre-infected. So you can notice that all 4 of these compartments can be exposed to COVID. Then you have infected here, and then you have recovered. The subscripts and superscripts have the following interpretations. So N is low risk. Right, so N, low risk and high risk. M has initial vaccination, second vaccination, or booster. A is the original strain of the disease, alpha is the original strain of the disease, and delta is the delta variant. Notice that E and I have 2 components each. This E and alpha is the individuals who have been exposed to the alpha variant. These are individuals who have been exposed to the delta variant. And these, of course, when EN develops into infection, this EN develops into infection in the alpha variant. This EN delta goes over to IN delta. There's no crossover between EN alpha, for instance, and IN delta. All right, so these go in parallel. We put it this way for convenience because really the EN alpha goes to IN alpha is parallel to EN delta goes to IN delta. All right? All right. So we define transition rates between the compartments. Okay, so those are these numbers here that are explained here. All right, let's start with beta. So for each L equals 0, 1, and each M equals 0, 1, 2, 3, beta NLM is a 2-vector whose 2 components express the infection rates due to IL alpha and IL delta respectively. All right, so let's try to understand this piece by piece. Notice that the L corresponds to the index on I. All right, the index on I gives low risk or high risk. Okay, these are the infecting populations. So L indicates the low risk and the high risk of the infecting populations. Notice that any low risk individual can be infected by low or high risk individuals. So that's why for N equals 0, for instance, we need infection from low risk and infection from high-risk individuals. Also notice that a low-risk individual could be infected either with alpha variant or delta variant. That's why we need beta to be a 2-vector, because when you transition from, say, S, you transition into this vector compartment. S could transmit into low risk into S could transmit into could go into a alpha variant exposed or delta variant exposed. So we need a 2-vector. This transition rate is a 2-vector. All right, because there are 2 possible outcomes here. So really you could think of this as 2 arrows in one. All right. All right. So we also have another index here. We have the 0, 1. This should be a 2 here, and then 3. Now that corresponds to the 4 compartments which can be exposed. These are the 4 compartments that can be exposed. And of course we already know that N is either low risk or high risk. These are the infected individuals. These are the exposed individuals. All right? So this here, so this sum means that some susceptibles are infected by low risk, some are infected by high risk. We need to add the effect of low risk and high risk infected individuals together. This beta, as I said, is a vector, and each beta is multiplied by the corresponding size of the infected population. We saw this before. The infection rate depends on the number of infected people, because if there are more infected people around, you're more likely to contact them. Now, what is this circle dot? This circle dot means that we're adding component-wise. This beta is a vector with 2 components. This I is a vector with 2 components. Sorry, backtrack there. Did I say adding component-wise? I should have said multiplying component-wise. This beta is a vector with 2 components. This I is a vector with 2 components. The first component of beta multiplies the first component of I, and those are the infections that lead to the alpha variant. The second component of beta multiplies the second component of I, and that gives the delta variant. So you could summarize this as ds dt equals negative. It's going to be a vector. You're going to have ds dt equals negative this here times s. All right, and that signifies that S transitions into 2 possible subcompartments of this compartment. All right, so the first subcompartment, alpha variant, second subcompartment, delta variant. And the same thing for all of these. Okay, now that's the most complicated one. The others will be easier. Next transition. So you can take some time to think about that. Next transition, this is not a vector transition, it's a scalar transition, it's a number. These are just the transitions from here to here to here. Like for instance, this is going to express that people who got their first dose will get their second dose at a certain rate and will get their third dose at a certain rate. Okay, so we have this transition, and this is overall vaccination rate. Okay. Of course, no one gets a second dose without first getting a first dose, so you have to go through this procedure. And no one gets a booster without getting a first dose. All right, so we've got the omegas. Let's go to the next one. Next one is delta. All right, delta means there's a rate of going from exposed to infected. The alpha variant goes to the alpha infected, and the delta exposed goes to the delta infected. All right. Next one is gamma. Now, gamma works a little bit differently. Both types of infected go to a single recovered compartment. All right. We're assuming that both, whether you recover from alpha or delta variant, it really doesn't matter. You've recovered from COVID. All right. The difference between alpha and delta variant is more the infectivity rather than the immunity. All right. So here we've got this I going to R. These 2 components collapse down to 1. So here you in fact have a scalar product. So you know a scalar product is indicated with the dot symbol. All right. And then rho takes Rn back to Sn, so it actually goes back around to here. We just don't want to make the diagram kind of junky, but this one goes here. So this is a scalar transition rate. This is a reversion rate. Recovered people do become susceptible again. That's been well documented in and observed. All right. Right. So here you use symbols dot and circle dot. Circle dot is component-wise multiplication, as I said. Okay. All right. Now, so the first exercise, you do everything. By the way, you'll do all your exercises in a Jupyter notebook. And the systems of equations can be typed into markdown cells using LaTeX. All right. You can see some examples of LaTeX formulas just by clicking into this cell. You can see that I've used LaTeX here. If you have no familiarity with LaTeX, a very easy way to use LaTeX is go to this one here. If I look at this here, you can construct formulas here. Here they have. This is like constructing formulas in Word. If I want to construct a sum, I do sum. And then here, if I want a sum that looks like, you can see how this works. It doesn't show very well. Here, let's do this one. Right? If I want to find the sum below and above, right? So you can do something like this. So I erase this. And then here I want to put something below, let's say A, and then here I put a B. And you'll see that the formula appears down here. All right, so you can build your equation this way. You just select this and paste it into your markdown cell in your notebook. Now, in markdown cell, if you look at how I've done this, you'll see that a LaTeX expression must be contained inside dollar signs. Actually, if you want an equation, you'd have two dollar signs. If I want an inline equation, so if I said, well, here, I'll show you this. All right. Suppose I wanted to make this an inline equation here. I can go down here and I'll make this $2 signs. And you'll see the difference. Right. See, that makes the equation an inline equation. I'm going to change it back because I like it the original way. So we'll just, is it going back? It's not going back. So go back like this. All right. All right. So you can see how to make your equations. Now there's a nicer way to do it, to line up the equations. I can show you that later. That's not important at the beginning. Just get the equations down there. Okay. So that's a way that you can enter LaTeX formulas. All right. So using the system diagram in the figure above, write the system of differential equations that describes the evolution of the system. Now look, since you've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, since you've got 10 arrows, you are going to have, well, actually you won't have 10 equations because you'll actually have one equation for each compartment, but you'll have one term for each arrow. So you have 1, 2, 3, 4, 5, 6, 7 compartments. 2 of these compartments are vectors. You can write these as vector differential equations. So you actually have 9 different 9 different components, but you should write this En as a single equation. That's why we collapse this into a single vector. Okay, so you should have 7 equations in these variables, S, V, E, I, and R. All right. So that's what this will do. Okay. All right. So that's exercise 1 here. Okay. So here, let me change this a little bit. I want to make this clear. I'll put this like this, so you can see what's going on here. All right, now actually you can see here how to do a equation. You can use begin equation and end equation. That's another way instead of using the double dollar sign. All right, so we'll do it like this. All right, so we're actually going to use a discrete model, not a continuous model. So instead of having time continuous, we'll have time come by an index. So discrete model will be obtained by replacing continuous time with the discrete index and derivatives with discrete differences. All right, so instead of x of t, which you'll have in your differential equation, you'll have x of j, where j is a time index. Instead of dx dt, you'll have x of j plus 1 minus x of j. So modify the differential equation that you gave in exercise 1 to give the equations for the corresponding discrete model. All right. So once you've got that set up, you're ready to go with Python. And that's the bulk of what you're going to be doing, is setting up the Python model. People had so much fun with the previous Python model, I thought we really had to do this again. All right. So first initialize tsim. Tsim is going to be the number of steps in the time simulation. So this is going to be number of time steps in simulation. Okay. All right. Now, you'll be creating classes. It's natural to create a separate class for each of the 2 subpopulations. All right. Each subpopulation will have 2 attributes. Okay. So okay, here, let me just say it this way. Instead of saying each subpopulation, we'll say the class. Okay, subpop. Okay. This class subpop has 2 attributes, params and vars. Why do we need params and vars? Well, because the equations have parameters, like the gamma, the delta, and so on, and they're variables, which are the s, r, v, and so on. And these attributes are both going to be classes in their own right, because params, we have several parameters, and variables, we have several variables. All right. So the params class will include all parameters, i.e. the transition rates. The vars class will contain all the variables. And so variables, I can say, i.e. compartments, right? Okay. All right. Now, note that each variable will be stored in an array with dimension tsim, because the value of the variable must be stored at each time, right? For the susceptibles, we're going to have to store 10 values for susceptibles. Okay, the vector variables will be two-dimensional. So the vector variables, like E, for instance, vector variables. So let's say let's see. Okay. Oh, I see. Yes. Okay. Okay. Yes. See. It says yes. Okay. For example, E will be a 2 by tsim array. All right. So this is going to be a attribute of the vars class, which itself is a subclass of subpop. All right, so it's going to be subpop.vars.e. So let me just write it that way. This is going to be subpop. Okay, that's how it's going to be arranged. All right. All right, now you'll also need to create instances L-risk and H-risk of this class. All right. So in this slide, it's all non-zero parameters to 0.05. I don't know what the values are, so we'll just make everything to be 0.05, 1 out of 20. All right, then you have a time loop, and then you put the discrete equations in the time loop. Okay, and you can say and build the variable arrays step by step. Okay, all right. All right, now, let me give an indication where we're going after this. This will be enough for this week, I think. But the assumptions that we've used so far are not realistic. Why is that? The model assumes the distribution of all transition times are exponential. In other words, any individual in any compartment has the same probability of moving to the next compartment, regardless of how long the individual has been there. This assumption is not good. For example, no one who has received the first vaccination will be vaccinated on the next day, right? But this assumption with exponential rates means that a constant proportion of the people in the compartment are vaccinated every day. That's certainly not true. For instance, if this, let's see if I can get this again. If this W was 0.05, that would mean that 1/20th of susceptibles are vaccinated. I'm sorry. So let's do this one here, from here to here. If this W was 0.05, that would mean 1/20th of this compartment is vaccinated every day. But no one is vaccinated a second time the day after the first vaccine. So it's not realistic. We want to use a different picture. All right. This here is kind of showing the diagram. I will explain this in another video. But if you set up the code this way, it will not be too difficult to modify to introduce these non-exponential rates. The important thing is to set up a good structure for your code. If you set up a good structure, then you can make changes and improvements that will capture more realism. All right, that's good. So we'll stop here.